Hello everyone, today in this video we'll be discussing the second module of DDCO super important questions from the exam point of view. And in this video I have selected 5 or 6 questions, and these questions are the most repeated one in the previous year paper, so don't miss any of them. And if you watch this video till the end, easily you can score more than 80% marks. And these questions are from the perspective that they have appeared in a single or, okay, not in a different or. There will be or, right, or question this or this. In the single or which is coming, anyways will be attending only one or, right? So the questions which have come in one of the ors, those all questions I have selected. So make sure you watch the video till the end, and please do like and subscribe. It helps me make more videos like this. And without wasting more time, let's get started. So the first question is, explain the working of 4-bit adder using 4 full adder. Okay, so individually also they can ask about the 4-bit adder, okay, but the more repeated one is 4 full ladder. Okay, so I'll be discussing that what is 4 full adder. Okay, this is pretty simple one. A 4-bit adder, also known as binary adder. Okay, what is a binary adder? It is a 4-bit adder. It is digital circuit that produces the arithmetic sum of two binary number. Let's take two binary number 101 and 110. The sum will calculate this and this and then this, like that will calculate, right? So for the 4 bits it will calculate. Okay, 10 10 11 11. It will calculate for 4 bits. That is called as 4-bit binary adder, and we are using 4 full adder, means for each calculation will be one adder, full adder. Okay, it can be constructed with full adders connected in cascade with the output carry from each full adder connected to the input carry of the next full adder. So there will be one full adder here, the output carry will be taken from here, and this will be having an input to the next one, and this will be generating another carry which will be connected with the next one. So each will have one input and output carry. Okay, interconnection of 4 full adders circuit to provide a 4-bit binary ripple carry adder. Okay, so see here we'll be having a0, a1, a2, a3. That is the first number. Okay, so a is denoting the first number, suppose 0 1 1 1. So this is a0, a1, a2, a3. Like that for the b also we'll be having 1 1 0 1, like that. B1 b2 b3, b0 b1 b2 b3, like that. So b0 and a0 will be calculating together, b1 and a1, a2 and b2, b3 and b3, and whatever we calculate we'll be getting a sum as well as a carry, right? That's how an adder works. So we'll be connecting this carry here, input carry, and this will also be considered along with these inputs, and a sum we will get, and we will get another carry. This will be cascaded, and we'll be finally getting one c4 also. So our answer will be this one: s3 s2 s3 s2 s1 s0. Okay, so arrange og end bits of A and add in bits of B are designated subscripts from the right to left, with subscript 0 denoting the least significant bit. Okay, so this is the first two bits we are taking for the two numbers, second 2 bits, third 2 bits, and the last bits. Okay, the carries are connected in a chain to the full letters to output the carry 4. Okay, so the carry 4 finally we'll be getting here, and when we do it in this way we'll be getting the answer. Okay, this is all what you have to write. Make this diagram and explain what's happening here. Okay, moving on to the second super important question, implement y is equal to y abcd, and the m values are given here using 16 is to 1 multiplexer and 8 is to 1 multiplexer. So multiplexer is very important. What does multiplexer do? It will accept 4 inputs and generate one of the 2 power n outputs. Okay, it will take n inputs and it will generate one of the 2 power n outputs based on a select line. Okay, so what is a select line also we'll be discussing. See, first they have asked about the 16 is to 1 multiplexer. Okay, so all what you have to do is make the truth table. What you will make? First you will make the truth table. ABCD you have written here, and this is the output y. Now based on these numbers, 0 is true, 1 is true, 6 is true, 7 is true, 8 is 9 is 10 11 12 14 is true. Wherever it is true you have to write those number here and mark it as 1 wherever it is true. So 0 1 is true, then we have 6 7 8 9 10 11 12, and then we have 14 as true. Rest all you will mark it as 0. Okay, after you have done that, what you have to do is, for the input 0 I am getting 1 here, for the input 1 I am getting 1 here, for the input 2 I am getting 0 here. So you have to make a diagram like this where you will be writing A B C D in one of the edges of the rectangle, and you will be writing 16 is to 1 mux. This is the input side. Okay, this is the input we will be getting from input from here. Calculation will be done, and we will be getting an output from here. Y will be the output. Okay, now what you have to do, wherever you have got 1, that you will be taking separately. Okay, this is 0, this is 1, this is 2, this is 3 4 5. So whichever has 1, all those you will be taking in a single line. Okay, it will be connected with 1. Wherever it was 0, all those you will be taking it as single one. as zeros connected together, and you will be writing here 0. This is all what you have to do for 16:1 marks. Now second question they had asked is 8:1 multiplexer. For 8:1 there is a problem. Why? Because there are 4 inputs here, but in 8:1 we can have only 3 inputs. Why we can have only 3 inputs? Because 2 power 3 outputs only can be happened, that is equal to 2 power 3 is 8, right? Only 8 outputs can happen, so we need to have 3 inputs only. So but we have 4 inputs here, so for changing that, what we will be doing is we'll be selecting D also here. Okay, D and Y we will be combining. Okay, what do I mean by D and Y combining? Now see, if you observe, you'll be taking 2 at a time. Okay, you'll be taking 2 of them at a time. Now the output always you'll be observing. If the output is same, okay, listen to me carefully. If the output is same, you'll write that same output. 1 and 1 I'll write here as 1, 0 and 0 I'll write here as 0, 0 and 0 I'll write here as 0, 1 and 1 I'll write here as 1, 1 and 1 I'll write here as 1, 1 and 1 I'll write here as 1, and here I have different. Here also I have different. Whenever you have different, what you have to do is observe the D value. Okay, observe the D value. Whenever you have different here, observe the D value. When this is 1, this is 0, that means it is reverse. Whenever it is 0, it is 1, that means it is reverse. Whenever it is reverse, what you will be doing is you will be writing D bar, okay, or D naught whenever it is reverse. In case if it was like this is different, but this is also 0, this is also 0, you will be directly writing here 0. In case if this was 1 and this was 1, you will be writing directly 1. But if it is reverse, you will be writing as D naught. In case if it is same, like for example, here it is 1, here also it is 1, here it is 0, here also it is 0, in that case you will write as D. Okay, that's the only thing you have to make difference. Now we have got D bar here and D bar here. Now this is the third input which we will be considering. Okay, this is the third input which we'll be considering, which you have got 1 0 0 1 1 1 D bar D bar. Okay, so this is the third output. What you have to do is you have to consider A, B, and then you have to consider this output. Okay, this output will be considered after taking C also. Okay, so A, B, C I have, and we'll ignore this one and we'll take this output. Okay, when it is 0 0 0, my output is 1. When it is 0 0 1, my output is 0. Okay, like that. So whenever it is 0, my output is 1 here. If it is 1, my output is 0 here, and so on. See, the thing you can observe here, 0 0 0 0 0 0, both are same. Both are same means this is 0. 0 0 1 0 0 1. When it is 1, I am having a one single output. When it is 0 1 0, I am having a single output, right? For 2, for 3, 4, 5, like that, it is divided now. Okay, so ABC value will be taking like this, A and BC here. Okay, so A 0 1 you will write. After that, BC 0 0 0 1 1 0 1 1. Now 0 0 0, what is 0 0 0? When A, B and C all are zeros, what is my answer? 1. When A, B, C both all are zeros, my answer is 1. Both of these will be same because we taken these two together. Okay, so it will be 1. When it is 0 1 1, my answer is 0, like that. When it is 0 0 1, my answer will be 0. Okay, 0 0 1, answer is 0. Is it 0? Yes, it is 0. Okay, so like that, 2 will be 0, 3 will be 1, 4 will be 1, like that. So we'll be filling it in according to that way, and all these values will be stored here. Next, after you have done this one, you'll be writing 8:1 mux. You'll be writing 3 inputs, 1 output here, and from here there will be 7 insertions. Okay, 7 insertions. The first insertion will be for 0 0 0. When the input is 0, what will be my output? Output will be 1. Okay, this is 1. Whenever it is 0 0 1 means 1. Whenever the input is 1, output is 0. So 1 will be taken with the 0 gang. Okay, and 0 1 0, it is 2. 2 also will be taken with the 0 gang. 0 1 1 1 1. Okay, so 3 will be taken with the 1 gang. Okay, so whatever the groups form, that will be taking it with that numbers. Okay, so 0 and 1 will be separated, and at last we have D bar also. So 6 and 7 will join D bar gang. Okay, so you got the point, right? If there is 4 inputs and we just have to have 8:1 mux, 8 you can write it as 2 power 3. At that time you'll get to know that I have A, B, C, D, and I just need 3 of them. So to change that, we'll be considering 2 at a time. At the last two at a time we'll consider and write 1 0 or D bar, and based on that we'll take ABC and that value, then another ABC, that value, skipping 2 at a time. Okay, like that we will do and make 8:1 mux. Okay, very important question from exam point of view. Next we have construct 8:1 mux using 2. So here we have to just use 2:1 muxes. Okay, so what we will be doing is, since we need 8 inputs, okay, 8:1 means 8 inputs and 1 output. 8 inputs, if you want to make it using 2 inputs, two, how many twos we will require? We'll require 4 twos, right? For a total of 8, we need 4 times 2 inputs. So we'll take 4 multiplexers here, 2:1, 2:1, 2:1, 2:1, and we'll give the inputs I0 till I7. Okay, and there will be one selector here. So if this is 0, I0 will be selected. If this value is 1 here, I1 will be selected. Okay, and whichever is selected, that will come here, and that will be passed here. Now, since we have 4 in 2:1 multiplexer, 8 inputs are there. There will be 4 outputs. 4 outputs means the input should be 2 and 2, right? The 2:1 mux will be here, 2:1 mux will be here. For the 4 outputs, that will be going as inputs. Okay, 2 here and 2 here. So 2 inputs will be going from here, again 2:1, and 2 inputs will be going from here, 2:1. Again we have 2 outputs here, that will be taken as input for the next mux, and another 2:1 mux we have to write here. And the two table we will make it as follows: 0 0 0 it will be I0, 0 0 1 it will be I1, and so on. All these things correspond to the output. If the output is I mean the S2, S1, S0 value is, if it is 0 0 0, this will be the input taken into consideration. 0 0 1, 0 1 0, 0 1 1, 100, 101, 110, 111. Okay, like that we'll be taking. Got my point? So after we have done it in this way, we'll be writing the outputs also I0 till I7. Okay, this is how we construct 8:1 mux using 2:1 mux. Okay, a variation can come, like for example, construct 16:1 mux using 8:1 mux and 4:1 mux only, or 32:1 mux using 2:1 mux and 8:1 mux. Like that, they can ask in any order, but the condition will remain same. First, observe how many inputs are present here. Based on that input, which how many of this type require. For 8 inputs, I require this 4 type. Okay, four copies of 2:1 mux. Then only I will be able to get 8 inputs. In the next one, I will require 2, and next I will require 1. Like that, we have to observe. Okay, how many we will be requiring. So we'll be making the diagram accordingly. Okay. So this was about the mux part. Moving on to the fourth super important question. Explain SR latch. First question, you have to explain SR means set reset latch and its application in switch bouncing. Okay, very important. This is most repeated question. And here observe carefully, they have asked latch, not flip flop. If you write about flip flop, you will be getting 0 marks. Okay, explain edge triggered D flip flop is the third question. First, let's understand what is SR latch. Okay, latch means hold. Okay, latch means hold. It will hold the value. If I make it as 0, it will keep on 0 until I explicitly make it as 1. Okay, so there will be a holding. Okay, the flip flop will be just reversing all the time. Okay, but latch will be holding it. Okay, so SR latch has two inputs. How many inputs are there? Two inputs, S and R. S means set, R means reset. It has two outputs, Q and Q bar, complement of Q. So there will be Q output, and when we reset it, whatever the output of Q was there, it will get reversed in Q bar. When S is asserted, Q is set to 1. Okay, when S becomes true, Q will become true. When R is true, at that time it will get reset, so Q's value will become 0. Okay, and Q bar will become 1. Q bar will become 1, Q is equal to 0. Both are same only. Okay, it is a reverse of this, so it is same. Now, this is the diagram we need to make. S and R, when both are 0, there will be no change in the previous output. Means there will be no change, and the previous output will be the current output also. So if I had Q is equal to 1 and I make S and R both as 0, set is also not happening, reset is also not happening. So Q will remain to be 1 only. Okay, Q will remain to be 1 only. In case I make S as 0 and R as 1, if I make R as 1, R means reset. Reset means Q will become 0 and Q naught will become 1. Okay, if I do the reverse, 1 and 0, Q will become 1 and Q naught will become 0. If I put set and reset together, it is forbidden state. It is just like switching on and off at the same time. Is it possible to switch on and off at the same time? Both on and off it can happen at the same time. No, the switches cannot happen on and off at the same time. So both of them I can't do set and reset. Both is not possible at the same time. Okay, either it will be set at a time or it will be reset at a time, or both will be not happening. Okay, that is possible. So this is the NOR gate diagram which you have to make here, and here will be the reset and here will be the set, and two NOR gates you'll be making, and you'll be making connection as follows: from here to here and from here to here. Okay, very simple. First make two NOR gates, reset, set, and here like this, here like this. Got my point? This will Q and Q bar. Here is the truth table. This is the same truth table as here. Here is a scenario. First we are doing S is equal to 1. When you do S is equal to 1, a Q will become 1, right? and R is 0, so Q0 will remain as 0. Both are 0 means it will still remain same. See, it is holding, it is a latch. It will not become 0 0. Once it is set, until it is reset, it will be 1 0. After that, when I click reset, this will become 0, this will become 1, and on 0 0 it will remain same. And if I try to do both at the same time, it will be a forbidden state, and then nothing will happen. Okay. So timing diagram of SR latch. This you have to make the timing diagram observing this one. Okay. So first see, S is true here. Okay, and S became false here, and reset became true here. So what happened at this point? Okay, observe at this point what is the value of Q. Q value is 1 here. Okay, this is 0, this is 1. Q value is 1 here. Okay, when set became 0 and reset became 1, Q became 0 and Q not became 1. Okay, I repeat here, when set became 0 and reset became 1, when reset is 1, Q naught should be true and Q should be 0. So Q changed its value to 0 and Q naught became 1, and this will remain as same until set will be true again. So reset again, it can go back, but whenever set will come up again, at that time Q's value will again change and Q naught value will be changed here. And after that, S can go back here also to 0, and again it can come here, but until reset comes true, this will value this and this value will not change. Okay, so it doesn't matter after setting S goes to 0. What matters is reset should come true, then only there will be a reset happened. Q not Q will become 0 and Q not will become 1. Okay, got the point. So latch will hold the values. SR latch is commonly used in electronic circuits to debounce a switch. Okay, meaning it eliminates the rapid on and off. For example, suppose that I have the control of S switch, and at this point what I do, I'll again on off on off on off on off. So will my output change? Reset is 0 only. Will my output change because of these fluctuations? No, because my output will only change when this will become 1. When reset will be clicked, then only some change will happen. Fluctuations here will not make any difference to this output here. Okay, that is why SR latch is used as to debounce a switch, mean it will eliminate the rapid on and off. Okay, when a switch is pressed, a signal is fed to set input, so it is set. SR latch which set the latch to specific state, it is set to a specific state. During the bouncing period, signal fluctuation might happen, but the latch will maintain its state, ignoring these temporary changes. Okay, so that was about the SR latch. Moving on to the edge trigger D flip flop. See, in flip flop, what happens? Whenever output comes here, it will be continuously changing. Okay, input came here, and because of clock, it will be continuously changing. So, how does this happen? Let's understand using this diagram here. So, in this diagram, there is a D latch here and another D latch here. And in D latch, as I told you, it holds the output, right? It holds the output. Now, here we have the input. D is the input. I can pass here as 1, I can pass, or 0. Both I can pass inside the D, and this D will be passing it to Y, and Y will be passing it to here, and this will be passing to Q. But it is not as simple as it sounds. Here another connection is made, EN. EN means enable. Enable means whenever enable is equal to 1, at that time only D will pass to Y. If enable is equal to 0, it will be stopped here in between. Okay, so enable depends on what? Enable depends on clock. Clock will be becoming 1, and it will become 0 after some time, again 1, again 0, again 1, again 0. So whenever it becomes 1, at that time it will come here and enable this one, and whatever input is coming from here, that will be stored here, and that will be passed to Y, and from Y it will be passed to this D. But from this D it will not get passed to Q in the same time, because when we had enabled this one, okay, clock is equal to 1, at that time this is enabled, so 1 will go here, and that will become 0, and 0 will come here and stay here. So 0 will stay here means this is disabled. This is disabled means whatever came from here, that will be stored here only, it will not change. When it will change, when clock will become 0 and this will be disabled, no more changes will be accepted from here. When 0 will be passed here, this will become 1, and when 1 will come here, this will be enabled, so the previous output will be shown here. Okay, like that. Alternatively, it will change the values. This is the working of master slave D flip flop. Okay, so there will be a master and a slave here. Circuit accepts D as the input and changes the output to Q only when the clock is negative or positive. Based on how we said, there can be two types of clock: positive edge and negative edge. Okay, this is a true table. When clock is 0, as you can observe, there is no change. If it is 0 or 1, it doesn't matter. Q will remain Q, Q naught will remain Q naught. When it is 1, if it is 0, this will become 0. If it is 1, this will become 1. And this is the reverse of it. Okay. So this was about the D trigger, edge triggered D flip flop. Okay. So a change in the output of a flip flop can only be changed only when there is a trigger in the clock. Trigger means either it became 1 or it became 0. At that time only change can happen. At that time it will remain constant. Okay. Got the point? Moving on to the fifth and last super important question of DDCO module 2, we have defined decoder. Okay, explain the working principle of 3 is to 8 decoder. Okay, what is a decoder? The definition we have to write. It is a combinational circuit. Okay, it is what? A combinational circuit. It converts binary information to from n input lines to maximum of 2 n output lines. So n input is coming and we are outputting 2 n lines. If n is equal to 3, 3 input came and output is 2 power 3, that is equal to 8 outputs. For 3 inputs 8 output will be there. That's why it is called 3 is to 8 decoder. Now 3 is to 8 decoder has 3 inputs xyz and 8 outputs d0 to d7. Based on the 3 inputs, one of the output is selected. Okay, so based on the values, if it is 0 1 0, one of the values among 0 to 7 will be selected. Okay, based on the combination of this. That's why it is called as combinational circuit. Truth table is shown as below. So here we have the xyz here. Based on what value of xyz we get, either this either among them will be selected. Okay, so xyz is here. If all are zeros, d naught will be selected. If it is 001, d1 will be selected. 010, d2 will be selected, and so on till the end. Okay, so this is the diagram, and the circuit diagram also you have to write for 3 to 8 decoder, and working principle is the same one. You can explain it in the same way. That much should be sufficient. Okay, that's all for this video, and please do like and subscribe. It helps me make more videos like this. And thank you so much for watching. I'll see you in the next one.